Hey everyone, today you're taking the ASVAB, and I thought you might want to see what it is that we were going to be doing in class today, because guess what? We don't have any extra days, so we need to make this day up, as it were. We have 3 days on areas, and this is our first day, the last section before our test, 8.2, and you'll remember that I had talked previously about finding area, and there were two things I had mentioned about it that are important in this section. Um, the first one is that uh, you want to watch out for total area. That means if there's any part of our curve that goes below the x-axis, you might want to subtract that integral and think about having a number of integrals to represent the total area. But we got around some of that by talking about situations. So this is the total area question. The net change, if I just integrated f from 0 to 8, I'd get 0, because this amount and this amount would cancel each other out. But if I want total area, then I have to do 1/2 4 times 2 minus this integral, which is 1/2 8 minus 4 times a height of -2. And so I end up with 4 plus 4, or 8, as the total area here. Okay, that's stuff we talked about before, but then we came to a situation like this one where I wanted to know the total area bounded by these curves. I had a curve up here and a curve down here, and this one went below the axis. It doesn't really matter. And we talked about adding up all these lengths to find the area between the two curves from A to B. And adding up those lengths meant taking this y value and subtracting this y value, or this y value and subtracting this y value. And so we summarize that by saying top minus bottom. I'm going to take the top function minus the bottom function, and I'm going to integrate from A to B. And that will work a lot of the time. So if we start thinking about this with this problem, find the area of the region bounded by y equals secant squared x, y equals sine x, x equals 0, and x equals pi over 4. And by the way, this is a problem without a calculator. I need to first think about what's going on. I've got my sine graph. Remember, that starts here and goes up to its maximum at pi over 2. But we're only going to pi over 4. And then we've got this secant graph. Remember, secant starts here at 0, 1, and secant goes up from there because it's reflecting that cosine. Remember, secant squared is just going to be a more amped up version of this. So I'm looking at this area. Well, to find this area, I do the top function, which is secant squared, minus the bottom function, which is sine, on 0 to pi over 4. So I would set up the integral secant squared x minus sine x dx from 0 to pi over 4. Well, I know that the antiderivative of secant squared is tangent x, the antiderivative of minus sine is plus cosine x, and I'm going from 0 to pi over 4. When I evaluate this function, at pi over 4, tangent of pi over 4 is 1. Cosine of pi over 4 is root 2 over 2. Minus tangent of 0 is 0. And cosine of 0 is 1. So 1 minus 1, they cancel, and I'm left with root 2 over 2, units squared. Okay? How about this one? Find the area of the region enclosed by y equals 2 minus x squared and y equals negative x. So, luckily we're all comfortable graphers. We know a downturn parabola that's been shifted up 2, root 2, negative root 2, and y equals negative x is here. So this is the area we're looking for. And so I want to think about it again as integrating the top function minus the bottom function, or the integral of 2 minus x squared minus the bottom function negative x. But from where to where? Where's this point? Where's this point? I know this point is between 0 and negative 1.4, and I know this point is bigger than 1.4. But how do I find them? Well, I'm going to have to do an algebraic substitution. Where I see y, I can replace it with negative x. So negative x equals 2 minus x squared. If I move everything onto one side of the equation, I get x squared minus x minus 2 equals 0, which means x minus 2 and x plus 1 equals 0. So this is negative 1 and this is positive 2, so my integral goes from negative 1 to positive 2. It's the integral of 2 minus x squared plus x dx from negative 1 to 2. Please don't forget to integrate at this point. Some people are doing that, where they're just now plugging these numbers into this function rather than into the antiderivative. Our antiderivative is 2x minus x to the third over 3 plus x squared over 2, and we want to evaluate from negative 1 to 2. When I plug in a 2, I get 4 minus 8 thirds. 4 divided by 2 is 2. Minus, I plug in a negative 1, I get negative 2. I get plus 1 third, and I get plus 1 half. I believe that's sufficient for AP free response. I'm going to take it a little further just to be sure. This will be 6, and that's 18 thirds minus 8 thirds is 10 thirds. And then over here, we've got 5 sixths minus 12 sixths is negative 7 sixths. So plus 7 sixths. So I get 27 sixths or 9 halves when I divide top and bottom by 3. I sort of feel like checking that one with my calculator to see what it gets. So I'm going to integrate math integral. We said 2 minus x squared plus x, comma, with respect to x from negative 1 to 2. 4.5. Nice. Okay, but you can expect to see these problems show up with calculator. Find the area of the region bounded by y equals cosine x and y equals x squared minus 1. No idea. Can't do that algebraically. I mean, I can graph it and say there's negative 1, there's positive 1, there's 1, cosine is 0 at pi over 2, and we've got symmetry. So, but where's that point? Where is it that cosine equals x squared minus 1? Shrug. I don't know. That's what calculators are for. You could, of course, integrate from this point to this point, or you could do 2 times the integral from 0 to that point of cosine x minus x squared minus 1 dx. And that's what I would do. But this is clearly a calculator problem because I need my calculator to find this point of intersection. So if I graph cosine x, and if I graph x squared minus 1, and if I take a moment just to make sure that my other functions are turned off, zoom 6, there's the cosine graph, here's my parabola, second calculate intersect, I get 1.1675. 1.1765. So then I want 2 times the integral from 0 to 1.1765 of cosine x minus x squared plus 1 dx. Please note that's plus 1 because I had to distribute the minus. So if I integrate f int cosine x minus x squared plus 1 comma x comma 0 comma 1.1765, and don't forget that's only half the region. We need to multiply that by 2. We get 3.11389 units squared. Okay, so there's that problem. Now, what about this? Region bounded by x equals y squared minus 4y and x equals 2y minus y squared. Okay, so what do those look like? Well, if I factor a y out of here, I get intercepts at 0 and 4. And if I factor y out of here, I get 2 minus y. Okay, this one goes this way, this one goes this way, and I'm looking for this region. Now, I have a problem with this region, and the problem is that if I do top minus bottom, I'm fine here, but over here, the top and the bottom are the same function, or the same curve. They're not a function because this fails the vertical line test. That happens over here as well, where the top and the bottom are the same. So I can't use top minus bottom here. I have to do something else. And so when I see x equals, that's a signal not to use top minus bottom. But instead to do right minus left. I'm going to take this right curve and I'm going to subtract the left curve to find those horizontal distances, and I'm going to add up these infinite number of horizontal distances. So I'm going to be integrating right minus left, and I'm going to see that from here to here. Now, I don't know where that point of intersection is. I know it's between 2 and 4, 3 maybe, but I don't know, so I'm going to have to find that. The right one is this parabola. That's this one. So I'm going to have 2y minus y squared. And then I'm going to subtract the left one, which is this parabola, or y squared minus 4y. I'm integrating from here, 0, to here. So I need to find that point of intersection. That's where this curve intersects this curve. Well, if this is supposed to be equal to this, I can set these equal to each other. So I'm going to have y squared minus 4y equals 2 minus y squared. Okay, well let's move everything on to, 2y minus y squared. Let's move everything onto one side. We'll have 2y squared minus 2y equals 0. Oh, I'm subtracting. That's minus 6. Good. It's good to do your basic math properly, Kukla. Factor out a 2y and get y minus 3. So y equals 0. We found that one. And y equals 3. So we're integrating from 0 to 3. I'm integrating 0 to 3 to y minus y squared plus 4y dy, which is the integral from 0 to 3 of 6y minus 2y squared dy. That'll be 3y squared minus 2y to the third over 3 from 0 to 3. 3 squared is 9. 9 times 3 is 27. 3 to the third is 27. Divided by 3 is 9. 9 times 2 is 18. And I end up with 9. My area here is 9. Okay, and I did that not with top minus bottom, but with right minus left. So if you see x equals, ta-da, you're going to probably be doing right minus left. Here's another one like that. We want the region bounded by x equals y squared minus 2, x equals e to the x, and the lines y equals 1 and y equals negative 1. Okay. I'm sorry, that says x equals e to the y, or you know that as y equals ln of x. So if I graph this situation, I've got this parabola with root 2, negative root 2, and negative 2. That's x equals y squared minus 2. And now we've got our ln of x graph. That's this one. And then we've got the line y equals 1 and y equals negative 1. And so we're looking for this region. And again, here's why top minus bottom doesn't work, because while top minus bottom here is a constant, top minus bottom here is using another function, and still over here when I do top minus bottom, I'm on the same curve. And so I would have to split this into 3 integrals, and I'm still troubled by how I would find this minus this on the same curve. So instead of doing top minus bottom, I'm going to do right minus left. I'm going to integrate this way. And I'm going to integrate from here to here. So I'm going to have the integral from negative 1 to 1 of the right curve, x equals e to the y, minus the left curve, x equals y squared minus 2 dy. Look, 1, we should be able to do this without a calculator. But 2, if you had to type this into your calculator, don't ask me how do I find dy. Your calculator doesn't care. it doesn't know that these are y's. You could just make them all be the same x, and your calculator will be fine. Okay, so what's the antiderivative here? It's e to the y minus y to the third over 3 plus 2y from negative 1 to 1. Okay, and that's going to be e minus 1/3 plus 2 minus e to the negative 1. That's going to be minus 1/3 times minus is plus 1/3 minus 2. So I'm going to end up with e minus 1 over e minus 2/3 plus 4. Okay, there's our region. No calculator needed. The last problem I wanted to look at with you today was this one. We want to find the region bounded by these two curves. Y equals x to the third plus 3x squared minus 4. And y equals negative 2x squared minus 2x minus 4. Okay. By the way, this one, and we don't know this, but I know this, this one is x plus 2 squared x minus 1, and this one is negative 2 x plus 2 x minus 1. Okay, I bring that up because we're going to graph these, and I don't think you'd see something like this on the non-calculator portion where you'd be expected to graph it by hand. I'm going to graph it by hand because I know what it looks like. We've got intercepts at negative 2 and 1. I guess negative 2 should be out here. This is negative 1, negative 2. For a sense of scale, we've got a downturn parabola that passes through those points. And then here we have this cubic function, negative at positive 1 and at negative 2. Ooh, at negative 2 there's a bounce. And it's a positive third degree polynomial, so I know I'm up over here and I'm bouncing here. And generally what people do here is they do top minus bottom. They integrate from negative 2 to 1. This parabola, negative 2x squared minus 2x minus 4, minus the bottom function, x to the third plus 3x squared minus 4 dx. And then they, dust off their hands and say, I'm all done. And then I mark half the points wrong on the test, and they're all upset. And I say, well, you didn't continue the graph. Because when we continue the graph, these intersect here at negative 4. I believe this is negative 8. I don't know what the y value is. But they intersect a second time. And so when they ask for the area bounded by the two curves, they want this as well. And notice this time, originally the down-pointing parabola was on top. Now the down-pointing parabola is the bottom curve. And so here I'm going to integrate from negative 4 to negative 2, x to the third plus 3x squared minus 4, subtract the bottom curve, negative 2x squared minus 2x minus 4 dx. So my total area is adding those two integrals together. Watch out for problems like this. Okay? Well, that's it for today. I hope ASVAB went well. And I'll see you tomorrow for more practice with this stuff. Okay, bye-bye.